who's going to be talking to us about exact and heuristic approaches for qubit routing on trapped ion quantum computers. So, floor is yours, Cal.
Okay, thank you for the introduction. Hello and welcome to my presentation on qubit routing approaches for QCCD trapped ion quantum computers. My name is Kyle Booth, and this is joint work with Bryan O'Gorman, Zhihui Wang, Davide Venturelli, and Eleanor Rieffel. So in this presentation, I will be introducing the quantum charge coupled device trapped ion quantum computer, discussing the characteristics unique to these devices in the context of qubit routing, providing a brief introduction to the paradigm of constraint programming, and then I'll be summarizing essentially our ongoing investigations into constraint programming based approaches for qubit routing on QCCD devices. First, I'd like to briefly review routing for superconducting devices, just to give you a little bit of a reminder. So the idea is that we're given a quantum circuit as illustrated on the left-hand side of the slide here. And what we'd like to ultimately do is take this circuit and compile it to be compliant on a quantum device of some kind. Here, for illustration purposes, I've included a 16-qubit Rigetti architecture. The idea in superconducting devices is that any pair of neighboring qubits can be used in a 2-qubit gate. And then any pair of neighboring qubits can also participate in a swap gate that moves these qubits around. So if we look at our circuit, we can see that we have a C0 involving the first and second qubit, as well as a C0 involving the third and fourth qubit. And these are readily implemented on the architecture at the beginning. However, when we look at this other C0, we see that it involves qubits that are not neighboring on the architecture. And so instead what we can do is we can actually use a swap gate between the neighboring qubits 2 and 3 to move qubit state 3 such that it is neighboring with 1, and then we can implement that C0. And so that gives you kind of a flavor or a view of how routing works in the superconducting case. So now I would like to look at QCCD trapped ion devices. And so this talk is based on an existing Honeywell device that was recently presented in this archive paper by Pino et al. The idea is that QCD trapped ion quantum computer is essentially a long linear array that's divided into different zones. So we have loading zones denoted in purple. This is where qubits, which actually represent ions, are loaded onto the array. We have storage zones represented by yellow and orange areas. And these are essentially zones that a qubit can be stored when it's not participating in an active operation of some kind. In this work, we're only going to look at yellow storage zones that are capable of holding a single qubit at a time. We also have gate zones indicated in blue, and these are zones within which we can implement some sort of quantum gate operation. And as illustrated, the gate zones are capable of holding up to 2 qubits at a time. And so once again, in this work, we're just going to be focused on routing with storage zones and gate zones. So there's 2 different types of operations that you can achieve on a QCD trapped ion device. The first are what are called transport operations. And so these involve actual physical manipulation of the qubits. And the second type of operation is a gate operation. So these are your typical quantum operations, and these happen in gate zones. So our first transport operation type is a linear transport. These can take place anywhere in the array. And the main idea is that we use these to reposition qubits across the linear array. So as the animation shows, we can take a qubit and move it from right to left, from one gate zone into another. And we can also take the other qubit and move it from a gate zone into a storage zone. The order of the qubits has to be maintained. So you can't use a linear transport to hop over one qubit. And these operations are typically very fast with very high fidelity. We also have swap operations that must take place inside gate zones. And essentially, these are, once again, physical manipulations that are used to switch the order of the 2 qubits involved. Lastly, there are split and combine operations that have to take place in gate zones only. The combine operation is essentially a preparation step that is required before we can implement any 2-qubit operation. And the split step, similarly, is essentially applied to a combined pair of qubits prior to any single qubit operation. So if we want to do a linear transport or a single qubit gate, we first have to split two qubits apart that have been combined. In terms of gate operations, we have a single qubit Z rotation that can be performed for free in software. We have single qubit XY rotations. These must be performed in gate zones. And a unique characteristic is that the qubit involved actually has to be isolated in the gate zone to perform this gate. And these can achieve arbitrary rotations in the XY plane. We're going to use this blue slash to illustrate these particular gates. And then finally, we have 2 qubit UZZ gates, which again must be accomplished in the gate zones. And once again, the qubits that are involved in these 2 qubit gates have to be combined beforehand with the combine operation. And we can use these UZZs to essentially synthesize any non-native 2 qubit gates involved in our circuit. And we're going to use this red X to illustrate these. And so now that you have an understanding of the operations available to us with QCCD trapped ion devices, we're going to look at an example routing solution. So I'm given an input circuit, the same one that we showed a few slides ago. In this talk, often I'm just going to talk about gates in terms of the qubits that are involved in the gate. So I'm kind of going to abstract away from the specific operation. So our gates are a gate expressed on 1, 2, a gate expressed on qubits 3 and 4. We have 2 single qubit gates and then another couple 2 qubit gates. And what we're looking to do is we're looking to essentially compile this circuit to the QCCD architecture. And so here what I'm showing is a subset of the total architecture I showed a few slides ago, consisting of 3 storage zones in yellow and 2 gate zones in blue. And for the purposes of the example, I'm going to abstract this figure a little bit so it's easier to understand. So again, we have yellow storage zones and blue gate zones. And what I've done in the initialization step is I've actually put qubits 1, 2, 3, and 4 such that they're arranged in this way. And so if we're actually looking to route the qubits to accomplish the circuit, in the first step, we can directly execute gates 1 and 2 and 3 and 4 as follows. In the second step, what we're going to do is we're first going to use our linear transport capability to isolate qubits 2 and 3 in their respective gate zones. And then we're going to implement the single qubit gates that involve those qubits. In step 3, what we're going to do is we're going to, again, use linear transports to put 2 and 3 in this first gate zone here. And then we're going to actually swap the order of 2 and 3. And so now we can see that their placements have been exchanged in step 4. What we're going to do is, again, use linear transports to bring everything into the gate zones and then execute our final two qubit gates. And so that's kind of a brief example of what routing looks like in this context. In this work, specifically, we seek to minimize the duration of the circuit. So ultimately, we want to be able to route this onto the architecture such that the compiled circuit takes as little time as possible. In order to minimize circuit duration, we need estimates of native gate durations. And then what we do is we basically aggregate the native gate durations into worst case durations for arbitrary 1 and 2 qubit gates. And so this table here is essentially illustrating the various operations available to us, as well as their duration in error. One thing that I want to note for trapped ion devices, kind of different than superconducting devices, is that decoherence times are typically much longer than the gate durations themselves. Thus, there's no strong link between the duration of the circuit and the fidelity of the circuit. As such, when we talk about minimizing circuit duration, this is primarily beneficial for increasing the throughput of repeated quantum experiments in academic or industrial settings. In terms of unique characteristics in QCCD routing, once again, quantum gates are only permitted in gate zones. Single qubit quantum gates require the qubit to be isolated in the gate zone. We have these linear transports that we can use to rearrange the qubits. And then we also have this combine and split operation that has to be considered. In terms of our approaches, we explore both exact and heuristic approaches for doing the routing. Due to the poor scalability of the exact methods, in this talk, we just focused on a constraint programming based heuristic. Our approaches, once again, seek to minimize circuit duration, and some key assumptions that we incorporate So we assume that these linear transports, because they're very fast, are essentially instantaneous. We append the split and combine operations as a post-processing step. So first we'll generate a circuit and then kind of greedily append the split combine operations at the end. And the last assumption is that we do not need, or we do not consider any ordering in the gates. So for example, they're fully commuting. This is a restriction that can be easily enforced with minor adjustments to the approach. But just for this work, we assume that the gates are not ordered in any way. And so once again, I said, we use this constraint programming approach to produce routings. To give you some background on what CP is, so constraint programming, or CP, is a paradigm used for modeling and solving hard constraint satisfaction problems. The modeling is done with decision variables, constraints, and an objective function, similar to things like integer and linear programming. And then the solving is actually accomplished via backtracking tree search, where we use this notion of inference to try and avoid doing a complete enumeration of the search tree. And we previously applied CP to quantum circuit compilation in the context of superconducting circuits a couple of years back. So please see that paper for more in-depth details if you're interested about CP. I wanted to give you a flavor of how problems are modeled in CP using, and I'm going to use Sudoku as an example. So the idea in Sudoku is that we actually have to fill each of these cells with a number 1 through 9, such that each row contains the numbers 1 through 9, each column contains the numbers 1 through 9, and each 3x3 grid contains the numbers 1 through 9. And so an interesting piece of information is that general n squared by n squared Sudoku puzzles are actually known to be NP complete. And so we can use CP to model this problem. Our decision variables are going to be xij, and that's going to be the value that's assigned to the cell at row I, column j. And then our constraints, so we encode the hints as constraints. So we say x11 is equal to 5, representing this guy on the top left. x12 is equal to 3, and so forth. And then what we're going to do is we're going to have these constraints of difference on the rows. So here we're saying that any given row has to have all of the values in that row have to take on different values. And then we impose a similar constraint for all of the columns. So we say each of the columns, all of the values have to be different. And then we impose a constraint on each 3x3 grid, saying all of the values in the 3x3 grid have to be different. And so this constitutes our CP model. And so what we're then going to do is we're going to take this model, I've just moved it into the lower left here, and we're going to employ backtracking tree search interleaved with logical inference to solve the problem. And so the general idea is we have at the root node, so picture yourself doing a Sudoku puzzle. At the root node, typically what you'll do is you'll try to make inferences. So we perform this logical inference, things like x13 cannot equal 3, x13 cannot equal 5, etc. And then if we run out of inferences to make and we're kind of stumped, what we might do is we might actually make a guess. And this is called a branch in terms of tree search. And so that means that we might guess that a 4 goes in this particular cell. And then we might perform more inference. So we say that x14 cannot equal 4. And what we might find is that our guess was actually incorrect. And so we kind of prune this subtree, do a backtrack, and then we're going to make the opposite guess. So we're going to say that x13 is not equal to 4. And we're going to perform more inference. And we're going to continue with this procedure essentially until the tree is fathomed and we can prove the CSP is infeasible or a feasible solution is found. And so the Sudokus you work on at home, likely you can complete them entirely with just using inference. You don't have to do any guessing, but there do exist Sudokus that do require branching, aka guessing. You may have run into a few of those in your travels. If you're new to Sudoku, I recommend you try them out because they're a lot of fun. So constraint programming, there's a number of different softwares. So these are essentially solvers, modeling and solving packages. IBM has one tied in with its Cplex library. I'm sure you've heard of Cplex before. Google has one in its OR tools library. And then there's other efforts like Minizinc, G-Code, and Choco that are also constraint programming, modeling, and solving softwares. And then, of course, on the integer programming side, you've probably heard of things like Gurobi and Express. One of the nice things is that the IBM Cplex Studio has both integer programming and CP solvers, so that's nice. Okay, so our CP approach for QCCD routing. So our goals for our heuristic CP-based approach are to produce high quality, so i.e. duration minimized QCCD routing solutions that provide reasonable scaling to larger instances. The modeling strategies to accomplish this, first, we're going to try and reduce the number of decision variables in our models by relaxing some of the problem characteristics and further constraining other characteristics. And then we're going to make sure we use the CP solver only to reason over the actual difficult problem characteristics. And we're going to evaluate any implicit elements by post-processing the solutions. And so this notion of implicit elements is something that I'll talk a little bit about more. Some of our key modeling strategies for the CP model is, instead of modeling locations of the qubits on the architecture explicitly, we're only going to consider the relative order of the qubits. So instead of keeping track of where everything is exactly on the architecture, we're just going to reason about the relative order of the qubits. The second idea is that we're going to discretize time. So from this continuous time representation into discretized time steps. And at each time step, basically what we can do is we can choose a set of gate operations to do in parallel, where the parallelism is actually bounded by the number of gate zones on the chip. And then the final idea is that we're going to implicitly model linear transports and swaps by essentially constraining the order of the qubits from one time step to the next. Specifically, we're only going to allow a qubit to move in the sequence, distance 1. So for example, if we look at time step 1 here, that has the order 1, 2, 3. The order 3, 2, 1 in the next time step is not allowed. However, the order 1, 3, 2 is allowed. And so what we're effectively doing is we're not directly modeling linear transports and swaps, but we're implicitly modeling them by limiting how far qubits can move from one time step to the next. Just to summarize the variables and constraints we use in our CP-based heuristic. So our variables are xqt, so this is the position of qubit q at time step t. ZGT is a binary variable, takes on a value of 1 if input circuit gate G is executed at time step t and 0 otherwise. Note that this is not talking about swap operations. This is only those gates as part of the input circuit. Our key constraints, so we ensure that for each time step, no qubits share the same position in the sequence. We ensure that all of the gates have to be executed. We ensure that, once again, so the permissible qubit movement in the sequence from one time step to the next, so the difference between their positions, if we take the absolute value of that, has to be, at most 1. So this essentially says that, a qubit can only jump at most 1 position from one time step to the next. We have a condition that says, if we apply a gate G at time step t, then we know that the 2 qubits involved in that gate have to actually be neighboring in the sequence. And then finally, we have the condition that, a given qubit can only be involved at most 1 gate per time step. So we can't actually, use that gate, that qubit more than once for a given time step. We explore 2 different objective functions. So you can imagine we're doing a backtracking optimization search, and we're going to try 2 different objective functions for that backtracking search. The first is a simple objective function. It doesn't actually consider gate duration at all. All it does is minimize the number of time steps used. And then what we're going to do is, after it's solved the problem, trying to minimize time steps, we're going to take that solution and calculate the resultant make span from the solution that it comes up with. So we have this variable d bounded below by this expression, which essentially is going to represent the end time of the last implemented ZGT gate. And so we're minimizing the total number of time steps used. Our second objective function is what I term a complex objective function. And this actually looks to minimize the circuit duration, also known as make span itself, by incorporating the durations of each time step, as well as the durations of those implicit swap operations. And so the math gets a little complicated. All I want to say here is that instead of just minimizing the number of time steps used, we're actually actively minimizing the duration of the circuit by analyzing what operations take place at each time step. In terms of our experimental setup, We use the Cplex Optimization Studio, the CP Optimizer Solver with default search and inference settings. And we perform tests on 3 different device sizes. So our small device has 3 storage zones, 2 gate zones for 7 total locations. And then we have a medium device and a large device with 5 storage zones, 4 gate zones, and 13 total locations. And so this table here kind of illustrates the instances we generate. Once again, we're working with abstract gates that have been assigned kind of a worst case duration based on the duration of the primitive gates on the previous table. And via this table, we can see like the largest problems we're solving involve, large architectures with 8 logical qubits and 30 gates. And what we're looking to do is basically compile that to the architecture. We have a total of 180 instances that we look at. In terms of the results, so the nice thing is that our heuristic produces valid qubit routings for all 180 instances. The results are based on a fixed runtime of 5 minutes. So this is the plot for the small instances. Each one of these points represents the results for a single instance, and the coordinate of the points are going to be the make span given by the simple objective function, and then the make span given by the experiments with the complex objective function. And so if a point lies right on this blue line, that means the make span using both objective functions was the same. If it lies below the line, that means using the complex objective function was actually better. And if it lies above the line, it means using the simple objective function was actually better. And so we can see for small problems, it's actually quite beneficial to use that complex objective function that reasons over the gate durations. For medium problems, as these problems get larger and the complex objective function gets harder to reason over, it starts to lose out over that simple reasoning. Remember, we're bounding our search by 5 minutes. And then, so these are mostly, as the problem sizes get larger, 20, 25, 30 gates. And then large problems, we can see that the advantage is quite a bit in favor of just doing the simple objective function that tries to minimize circuit depth. And so once again, complex objective, valuable for smaller problems, less so for larger problems. Some observations, relaxing elements of the problem improve scalability at the expense of optimality. Our approach does sacrifice some potential parallelism due to this implicit swap layer. The use of time steps might erode utilization if the gate durations are highly variable. And then so we're looking to address some of these aspects in part of our ongoing work. And once again, we actually have to post-process our solutions to translate our heuristic into an architecture-grounded solution. In terms of conclusions, I just wanted to say with modeling adjustments, we can use these tree search-based techniques in a more scalable fashion. Our CP heuristic was able to solve problems with up to 8 logical qubits and 30 gates on a fairly large architecture. And then as part of ongoing work, we're looking to investigate the extent to which our heuristic scales, as well as explore maybe warm starting exact models using solutions produced by this heuristic approach. And a paper is coming soon. And that's all I have for you today. Thanks for being a great audience.
Thanks, Kyle. So I have a quick, I know you just said that this is sort of future work, but as a kind of perhaps a preview, do you have any sense of like scalability of these methods for like larger devices? Like, is it really gonna require some like really new like methods, or
Yeah, so this is a good question. Yeah, so most of my research revolves around these tree search-based techniques, right? And one kind of drawback to a tree search-based technique is you need to represent all of the variables and constraints up front. And so that can often make these models prohibitively large. So I outlined a few strategies you can use to try and make the models more smaller. And from what I'm seeing right now with experiments, the scalability does seem reasonable. There will end up being a point where the models are prohibitively large, and even finding a feasible solution takes too long. So never mind optimizing, just finding a solution that satisfies the initial CSP before optimizing the objective just takes too long. So within the field so my background is in operations research, and within this field, there do exist techniques for trying to scale better through like the lazy introduction of constraints and variables. So you have row generation techniques, column generation techniques. And so part of my ongoing research involves looking into these more sophisticated decompositions and trying to figure out how they can fit in with work on qubit routing.
I see. Okay, so there's a few questions that have come up on the Slack channel, so I'm going to go through them sort of chronologically, and then we'll see how many we can get through. So the first one is from Ross Duncan. So he says that CSP is one of these things which is basically infeasible in general, but can be pretty good in practice. And it looks like you looked at basically a hard case. Do you have any sense of the asymptotic complexity?
So we're currently working on a formal, complexity class assignment to this problem. We suspect it's NP complete. So there exist various proofs in literature that, qubit routing swapping for superconducting architectures is NP complete. I suspect a similar situation is involved here, but we haven't actually formally proven this yet. So.
Got it. Okay, second one. It's very fun. I feel like a bit of an actor actually relaying these questions. So second question from Ling Ling Lao. Well, it might actually be related to the first one. So the question here is, can you explain a bit more about how the complexity of the CP heuristic scales with device size and circuit size? Like, do you have any sense of this relation?
So yeah, I feel like I sort of already commented on that. So a couple assumptions. If we assume, first of all, that qubit routing for this problem definition is an NP complete problem, then, applying a tree search based CP search to our model, in the worst case, we might have to enumerate the entire tree. Fortunately, in practice, that almost never happens because of the logical inference we perform at each of the nodes. But again, assuming this is a hard problem, we're using a tree search based technique. Asymptotic complexity would have us explore the whole tree before finding the optimal solution. In practice, this very, very, very rarely happens. And indeed, I didn't really talk about it in the results, but for a lot of the experimental runs, the search was actually finding and improving the optimal solution. One of the nice things about tree search techniques is that just because you can't find and prove the optimal solution doesn't mean they're not useful. So they're anytime, in the sense that, if your budget is 10 minutes, you can let the search run for 10 minutes and then just take the best thing it found at the end of 10 minutes. Another benefit is that, you can incorporate additional constraints into your models fairly easily instead of, having to, write your own checking algorithms and all this from scratch. So I'm a personal believer that these model and solve paradigms are really useful for, kind of ease of use or algorithm development, these sorts of things. But to summarize, in the worst case, yes, these are exponential algorithms, assuming the underlying problem is hard, and the tree search to find and improve that optimal solution could take a very, very long time. So. Right.
I mean, in a way, this is kind of the name of the game in compiling, I suppose. So.
Yeah. I mean, most of the approaches that I read in the literature have like time-bounded heuristics that try to, it's like local search schemes that take a given solution and kind of, rearrange them and these sorts of things. One of the drawbacks is that you don't actually have an active bound on the optimal solution, and so you don't know when to stop. One of the nice things about tree search techniques is that both, modern IP solvers and CP solvers are also kind of constantly building this this lower bound as the search progresses, and at some point they terminate with a proof for the optimality of the solution. So assuming that that your model can actually be represented reasonably, then you have a really nice property where you're also building these anytime lower bounds. So.
Right. So in fact, you've now touched like a few times on this next question, but I'll ask it anyways. Do you know how close your solution is to the optimum?
So that's a good question. I'm working on that right now. So the problem is the heuristic. So if you try, one way to find the optimal solution is essentially to encode the original problem with no relaxations as an integer program, and then just let the integer program run until it finds and proves the optimal solution. You can be confident it's optimal, and then you use that as kind of like a bound to form your optimality gap. The short answer is that I don't actually know how far these are from the optimal solutions. The idea with experimenting with the two objective functions was to try and give some sort of comparison when we reason about the specific durations of the gates versus when we don't. But no, this is part of ongoing work, is to try and, at least for the small problems, develop proofs for the optimal solutions so we can compare our heuristics to those.
Got it. Okay, great. And so here's one last question. So the question is, you mentioned that the fully commuting gate assumption can easily be removed. Can you give an indication as to how that would be done?
Yeah, so so a lot of the work that's kind of done in our group and whatnot are on algorithms such as QAOA that have a lot of commuting gates. And so kind of enforcing these very strict orderings on the gates in the circuit doesn't necessarily make sense. However, I recognize that there are a lot of cases in which you'll want to do this, at least over a portion of the circuit. And so the way that you can adjust the approach to incorporate these orderings is just through constraints, right? So we can essentially say that a given gate G has to be activated at a time t before given gate G prime or something like this, right? And so as part of my code, I actually have an optional run flag that allows you to preserve the order of the gates that is encoded in the problem definition. I haven't actually done an analysis to see if this dramatically affects results or not. And in fact, if there is a strict ordering across all of the gates, then the problem itself becomes much, much simpler, because then all you're looking at doing is trying to come up with the minimum kind of linear transport swap problem between two given gates, right? Whereas in this case, we're actually allowing the order of the gates to be flexible as well. So we're solving a problem that is potentially quite a bit harder than just looking at the routing in between the layers. Yeah.
I see. Okay, maybe we can stop here for now, but I see that the discussion is ongoing on Slack, so you might want to partake in some of these conversations there. But thanks a lot for a great talk.
For sure, I'll check in. Thanks very much.